here we are determining the end behavior of a polynomial function. Now, what is end behavior? Well, end behavior is the general direction that a function is going to follow as the x values are becoming infinitely large or infinitely small. Now, to help us in describing the end behavior of a polynomial function, or any function for that matter, we need to establish some new notation for infinite end behavior. So our first new notation is x approaches infinity. So in other words, we have that x is growing infinitely large in the positive direction. So our next new notation is x is approaching negative infinity. So what does this mean? Well, if x is approaching negative infinity, then x is becoming infinitely large in the negative direction. So these are our two new notations for x, but what about y? So similarly to case 1, we now have f of x is approaching infinity, or positive infinity. So with case 3, this notation implies that the y values are growing infinitely large in the positive direction without bound. And last but not least, so in our last case, we have that f of x is approaching negative infinity. So in this case, we have that the y values are going infinitely small in the negative direction. So in other words, these values of y are decreasing without bound. So now that we've established new notation for infinite end behavior, let's go ahead and see how this applies to polynomial functions. So continuing with our explorations of end behavior of polynomial functions, we can observe that as x is approaching positive infinity, or as x approaches negative infinity, the function is going to increase forever or decrease forever. And in general, is going to follow the general behavior of the polynomial function's leading term. So this is what leads us to the leading term test, which is going to allow us to classify the end behavior of a polynomial function. So to get us started, let's consider some arbitrary polynomial function. And I want to point out the very first term in the sequence. This is our leading term. So as x is approaching positive infinity, or as x approaches negative infinity, the graph of the polynomial function is going to behave in a general manner that is the same as our leading term. So when we're identifying the leading term, we want to make note of the degree, or our power of n. And we also want to make note of that leading coefficient, so the constant attached to the variable of highest degree. Now, we can classify polynomial functions into even functions and odd functions, or even degree polynomials and odd degree polynomials. And then depending upon the value of that leading coefficient is going to determine how the ends of the graph will behave. So let's start by considering even polynomials. So when we're working with even degree polynomials, we can keep in mind that n is even. So powers like 2, 4, 6, 8, and beyond. Now, if n is even, then our leading coefficient can either be positive or negative. So when we're working with an even degree polynomial that has a positive leading coefficient, then we can conclude that both ends of the graph are going to point up, like the parabola. So, for example, while we don't know what's going on in between the ends, since we have an even degree with a positive leading coefficient, we know both ends are rising up or growing, increasing without bound. So we can observe on the left-hand side that as x is approaching negative infinity, the corresponding y values are growing without bound. Or as x approaches negative infinity, f of x is approaching positive infinity. And on the right-hand side, again, we can see as x is growing or approaching infinity, the y values are also approaching infinity. So this is the case when we have a positive leading coefficient, but what about when we have a negative leading coefficient? So when we're working with an even degree polynomial with a leading coefficient that's negative or less than 0, we can conclude that both ends of the graph are going to fall down. And connecting this to infinite end behavior, we can observe here that as x is approaching negative infinity or getting smaller and smaller, the corresponding y values are getting infinitely small or decreasing forever. Now moving to the right-hand side, again, we can observe here that as x is getting infinitely large or approaching infinity, the corresponding y values are decreasing without bound. So these are the end behaviors for even degree polynomials, but what about odd degree polynomials? So continuing with our leading term test, we now need to consider the end behavior of a polynomial function when we're working with odd degree polynomials. So in other words, here we're only considering cases where n is odd. Now, just like with even degree polynomials, once we identify that we're working with an odd degree polynomial, we then want to consider what is the value of our leading coefficient, or in other words, the constant attached to the variable of the highest degree. So case 1. So if we have a positive leading coefficient with an odd degree, the leading term test lets us know that the left-hand side of the graph will fall and the right-hand side of the graph rises up. So again, while we're not sure what's going on in between yet, we can make some observations about the end behavior of this graph. So looking on the left, we can see that as x is approaching negative infinity, the corresponding y values are decreasing without bound. And over on the right-hand side, we can see here that as x is growing infinitely big, the corresponding y values are also approaching positive infinity. Now, this is the case for positive leading coefficients. And what about the case for negative leading coefficients? So in the case when we're working with an odd degree polynomial with a negative leading coefficient, we can observe that the left-hand side of the graph is going to rise or increase forever, and the right-hand side of the graph is going to fall or decrease forever. So more formally, we can observe that as x is approaching negative infinity, the corresponding y values are approaching positive infinity. And on the right-hand side, we can see that as x is approaching positive infinity, the y values are approaching negative infinity or decreasing forever.